It's Marcus Strom speaking on the philosophy and science. Is Marxism compatible with emerging new physics?
Good morning, comrades and friends. Thank you for joining this. I hope this doesn't go over, but I've tried to cram far too much into this talk. Not quite the singularity of all mass at the time of the Big Bang, but it felt a bit like that when I was preparing it. So 100 years ago this year, French aristocrat Louis-Victor Pierre Ramond, the seventh Duc de Broglie, presented a new hypothesis in physics. It's in there. He said it wasn't just light, but also electrons and indeed all of matter that exhibited the properties of waves. In doing so, he upended millennia of thought. Just 3 years later, his hypothesis was proved in experiment, and in 1929, he received the Nobel Prize for Physics for discovering the wave nature of electrons. So from 1924-5, when his PhD was published, to 1927, it's 29, still one of the fastest PhDs to Nobel Prize. I think maybe the fastest PhD to Nobel Prize there has been. Einstein, this guy had a reputation of being a bit lazy, didn't quite know what he was doing with his PhD. So his PhD supervisor said to him, "Look, time's ticking, deadline. Anyway, I've arranged for Einstein to be one of your examiners." You know, okay, I better pull something out of my ass for this. So when Einstein wrote to a colleague of the thesis, he has lifted a corner of the Great Veil. It's not bad for a PhD thesis review, is it? So de Broglie built on the work of Max Planck and Albert Einstein. You might recognize that. Albert Einstein equals mc squared. That's Planck, which is the relationship between the frequency of light and its energy, mitigated by the Planck constant. And he did a bit of Higgs-Popery, and from that you can work out the wavelength of an electron. So this discovery opened the floodgates. Within 3 years, quantum mechanics was born. This was on top of Einstein's other great contribution, general relativity, overturning the gravitational theory established by Newton. A century later, now, these great physical theories, they're the pillars of our knowledge of the universe, quantum mechanics and general relativity. They've been shown again and again in experiment they are correct as far as experimental science can tell. Yet they are fundamentally incompatible with each other. Further, physicists do not agree with each other on what quantum mechanics means in terms of our understanding of matter and the reality of the universe. And our theory of gravity remains incomplete. Is quantum mechanics merely a highly accurate mathematical formalism, or is it a physical description? Does the wave that described by the Schrödinger equation actually exist? This is unclear, contested, and there's a complete lack of agreement. The so-called Copenhagen interpretation of quantum mechanics, so-called because Niels Bohr, the great Danish physicist, championed it in the 1920s and 30s. It incorporates the wave-particle duality as just a given that you can't contest. And it assigns properties to quantum objects only as a result of measurement. The subjective act of measuring something creates the outcome. Or is there something much more that we don't understand, as Einstein argued to the end of his life? This morning, I want to look at whether that revolution in physical science in the past centuries undermined materialism and what the non-determinism implicit and the non-localism implicit in quantum mechanics means for the future of our knowledge of science. So I will argue that matter is fundamentally a relationship. You cannot understand matter without understanding it as a totality. Inherent in matter, and by that I mean mass and energy, are interrelationships, sometimes as unity of opposites. So E equals mc squared. Matter does not exist in isolation. However, the methodology of much of modern physics is about trying to isolate physical systems to understand them better. Matter is in constant motion. You've got Brownian motion, which you might know if you look very closely at water, you'll just see constant particles moving, and this is just matter constantly bombarding each other. Even the quantum ground state of an object, you put something to its lowest possible energy, it still moves, even though it has zero energy. What's going on there? This is all being measured. Constant motion can be thought of a state of constantly becoming rather than being, and this goes back to Heraclitus in 500 BC. This is in opposition to the Aristotelian view, Aristotle argued the natural state of matter is at rest. And that was actually upended by Newton fundamentally. The quantum motion of matter is non-deterministic, it's completely randomized, but at classical levels, large levels, it becomes deterministic. We still don't know why or how that happens. So with non-determinism and non-localism, I'll explain, you can ask questions about what that means. What it seems to be is that not everything we know about a physical system is localized. Now, Einstein had trouble with this. It's a very counterintuitive idea. It explains something called quantum entanglement. Matter and reality exist independently of our consciousness. That sounds uncontroversial, but many physicists don't agree with this. And while absolute truth does exist in reality and the world is knowable, our knowledge can never be final. And I would say that there has been a constant battle in natural philosophy between idealists and materialists, between the proponents of matter in stasis, as Parmenides argued, and matter in constant flux. I think that argument is still ongoing. So I want to start off by just showing two experiments. I tried to work it out, it's too hard, but a couple of very short videos.
How beautiful is this? This is an experiment in quantum mechanics called the double slit experiment. But I really didn't expect to see this when I did it myself.
No.
And seeing this changed my mind on an important question in physics. What is light? But before all that, how beautiful.
You don't need to start it.
Strom experiment performed in 1922.
Can go back.
You've moved to the next slide.
Sorry. It's because I'm not in front of it.
Yeah,
I can only
just go
do
back.
so many things at the same time.
Beautiful.
Just leave it.
This is an experiment in quantum mechanics called the double slit experiment. I really didn't expect to see this when I did it myself. And seeing this changed my mind on an important question in physics. What is light? But before all that, here's a simple experiment that you can do. All you'll need is a laser pointer and a strand of hair. So if I just take this laser and I shine it at this whiteboard here, you can see that you just get a dot. But what do you reckon will happen if I put this hair in the way? You might expect the dot to get split into two dots, or for there to be a dark line through the dot, or nothing at all to happen since the hair is so small. But let me show you what actually happens in the dark because it looks really impressive. Surprising, right? And it's nothing to do with the hair itself. You can do the exact same experiment with anything thin. This is a variation on the double slit experiment, which is an experiment that's so important. You learn about it of pretty much day one of any Quantum 101 class. The normal way to do the experiment is to shine a light on two very narrow slits. Then the light that goes through the left or to the right. This variation is pretty much the same. The light goes through one way or the other. But besides being easier to do this way, the other advantage is the pattern you get. You can see that they both have the same sort of flavor, but they're different. For example, the dashes of light for the hair version are all evenly spaced and get lighter as we go. But the dots of the double slit are much more patchy. That's because of something called single slit interference, which is basically a distraction in this scenario. So yeah, I kind of prefer the hair version. Plus check this out. I'm using this smoke in a can stuff to see the actual beam, but look really closely at the beam. You can actually see where the hair splits the light into two. How crazy is that? And looking at this, I think it's really hard to understand why you get the crazy double slit pattern when it seems like obviously you should just get a dot with a line through it.
So you don't, because the energy from the light is both acting as particles, photons, wave packets, wavicles, and it's also creating an interference pattern. Like if you put two stones into water and you see the waves interact, and it creates that pattern against the wall. So this is called wave particle duality. And that shows that fundamental thing. The next one is a bit more, hopefully that's pretty straightforward to understand, although we don't know what's going on. The next one is to show the
How?
this one.
The Stern-Gerlach experiment, performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. The researchers observed that the beam was split in two possible states, which were later named spin up and spin down. How can this be explained?
So what that means is that a spin, it's not actually a spin, it is the angular momentum of an electron, and as it moves, it's like a little magnet. It's like electrons are like a little bar magnet, and the spin is either up or down. It's completely quantized. It can't be in any other direction as it goes through a magnetic field. Now, what is interesting about this is if you put it through one of these experiments, you set the electron, it will always be measured as spin up. If you split that beam and you put those electrons and you measure it again, they will always be spin up. If you then scramble it by measuring its axis going the other way to try and work out what its spin will be along that axis, you would expect it to be zero because it doesn't have any spin in that direction. But again, you either get up or down. But if you were to do that 2 million times, you get 1 million approximately up, 1 million approximately down. On average, it is zero. So although as you measure one thing, it is completely quantized, on average, it acts as you would expect it to in a classical world. That we don't know why. How do the electrons know to average themselves out? We don't know. So matter is not deterministic, but it averages out that way at large scale. So when you bounce a ball, like if you throw a ball at a wall, it doesn't go through the wall. It comes off in predictable ways. So let me use an analogy. It's always very dangerous to use these sorts of analogies outside physical science because they break down, and there's a whole generation of people earning sinecures talking about quantum effects in diplomacy, global entanglement. It's all bullshit, but there is a whole academic field dedicated to it, social science trying to use this. But the analogy I will use, so if interest rates go up, I don't know what you're going to do. I don't know what you're going to do, whether you're going to go out and party, whether you're going to cry, sell your house. I don't know what you're going to do. But on average, we can expect consumption to drop in an economy if the interest rates go up. So on average, you can make predictions, but the individual person it's random how they're going to respond. Although it's not completely random because you can go and interview someone. So it's still deterministic, unlike quantum. In quantum, it really is completely random. Now, most quantum theorists and practitioners just accept this about matter and say that they avoid asking questions about the true nature. They just accept it as a practical recipe for an observer to predict the probabilities of measurement outcomes. And they're the most accurate measurements you can get. So also, in more developed, electrons, for example, particles or waves? Well, our current theory says they're actually excitations of the electromagnetic field, and this T-shirt kind of explains that in a way. But we're hampered because we use classical language and classical descriptions for non-classical objects. It's like trying to explain a platypus by saying it's a cross between a beaver and a duck. Like, it's not, it's a platypus. So Philip Ball, who's a great science writer, some of you may know him, he's British, talks about a historian, Mary Marabella, who says that wave-particle duality is neither unambiguous nor necessary in theoretical research. It's a probability measurement. It's like a smear of an electron. Where will you find it? The calculus of the Schrodinger equation, which describes the wave, is formally analogous to a kind of wave equation. But a wave of what? Is it a physical thing? Is it a density? Is it a field? But it's definitely a probability. So wave-particle duality was essential for Niels Bohr's complementarity. He just said, you've got to accept sometimes it's this, sometimes it's that, and don't ask questions. And I think my next slide is. So this was a paper published this year, which allegedly shows a quantum of electron morphing into a wave. Now, a lot of people are saying this is bullshit. This is just a photo of some atoms, sorry. And is this morphing into a wave? Some people are claiming it is, some of it aren't, but it is clearly trying to apply classical terms to quantum objects.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he was the guy that caught on before he wrote the paper. But after people read it, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. I do appreciate this, and don't take the lecture too seriously. You really have to understand in terms of some model what I'm going to describe. And just relax and enjoy it. I'm going to tell you what needs to behave like. If you will simply admit that maybe she does behave like this, you will find her a delightful and trim and thing. So that's the way to look at the lecture, not to try to understand. Well, yeah, understand English, of course. But in any sense, in terms of something else, don't keep saying to yourself, you can possibly afford it, but how can it be like that? But you get down the drain, you get down into a blank analysis, which nobody has yet escaped, nobody knows how it can be like.
So that's Richard Feynman, who's one of the greatest physicists of the second half of the 20th century. And you see in there, he's a hugely successful popularizer of quantum mechanics to undergrads, and his lectures in the 50s and 60s worth looking at. But there he is, basically saying, don't ask the questions. We don't understand. And so maybe it's true, but this whole culture from Niels Bohr, Feynman, and others is to put a lid on exploring quantum foundations. Now, my argument today is that we should not be concerned about the non-determinism and non-localism inherent in our understanding of matter. While we are materialists and understand cause and effect, we're not teleologists. Our materialism is not mechanical. I also state that while quantum mechanics is, as often said, argued the most successful predictive theory humans have ever developed in physical sciences, it is clearly incomplete. Niels Bohr and his co-thinkers might say, shut up and calculate when it comes to quantum mechanics. And that's repeated by this kind of attitude, but it is fair to say they never shut up about it. And neither should those who want to establish a deeper materialist understanding of a physical reality. Now, Einstein was one of these people. Right? There he is. Einstein, Max Born was a proponent of the Copenhagen interpretation. There's masses of correspondence and articles about this. I did have a big bit in here about this is in complete conflict with the way the Trotskyist and Stalinist movement do knowledge. This is all open, debated, huge conferences. We know what people thought and what they argued. So the wave function, describing the wave nature of it, does not describe the totality of what really pertains to the partial system, rather only what we know about it in this particular case. I'm therefore inclined to believe that the description of quantum mechanics has to be regarded as an incomplete and indirect description of reality. That was Einstein in 1948, spent the rest of his life trying to come up with something better and couldn't. And but today it feels like we are on the edge of another round of discoveries, both in quantum, but also in relativity, dark matter, dark energy, cosmology. Scientific knowledge appears to emerge in phases of punctuated equilibrium, to borrow from Stephen Jay Gould. There are long periods where it feels knowledge is final, with short periods of revolutionary upheaval, and 100 years ago was clearly one of them. Lord Kelvin, given the temperature scale Kelvin, there is nothing new to be discovered in physics now. All that remains is more and more precise measurement, he's alleged to have said in 1900, except he didn't. I don't know, this persists that he said it, but this is probably taken from a guy called Albert Michelson, an American experimental physicist, who proved that the ether didn't exist. He said it's probably that most of the grand underlying principles of physics have been firmly established, and that the future truths of physical sciences are to be looked for in the 6th place of decimals. Now, this is before Planck and Einstein launched their revolution of knowledge, physical knowledge. But Lord Kelvin doesn't get off lightly, because he also said this in 1902. Neither the balloon nor the aeroplane or the gliding machine will be a practical success. So what this means is it's really hard to make prediction, particularly about the future, as Niels Bohr never said either, although he's attributed with it. Apparently it's an old Danish saying. So from the foundations of quantum mechanics a century ago to the building of the atomic bombs, a great war raged between the realists, what we would call materialists, the realists led by Einstein, and the anti-realists led by Niels Bohr. It's commonly thought, if you talk to most physicists, quantum physicists, that Bohr won the debate and we're just getting on with the science, and that the experimental proof of non-locality, the fact that in quantum mechanics violates the assumptions that things interact only with things that are near them in space, that has been proven not to be true, put Einstein's ideas to bed. But this is far from the case. In Philip Bohr's book Beyond Weird, which is worth reading, fairly recent, University of Massachusetts physicist Chris Fuchs said in 2002, and this will be familiar to a lot of us, any meeting on the fundamental principles of quantum mechanics is like being in a holy city in great tumult. You will find all the religions with their priests pitted in holy war. Now, I think this holy war is part of a tussle that has gone on since antiquity between those who uphold the primacy of matter and those who are either agnostic, like someone like Heisenberg, operationalist, utilitarian, or outright idealist in their approach to matter, energy, and knowledge. So in 1927, this all came together in the Solvay. Oh, no. Where did the Solvay go? There. There it is. I put it somewhere I didn't expect it to be. So this conference, Solvay 1927, all the big brains of the physical revolution are there. Einstein, Planck, Curie, Lorentz, Broglie, Born, etc., etc. I mean, and they all argued about what the fuck is matter. Now we've got this quantum mechanics, and that has not been resolved. That's all going the wrong way. Excuse me. Right, so back to the scientific holy war. Now, what is matter? Given that Marxism is a philosophy and social science of dialectical and historical materialism, understanding what matter is, or at least our approach to it, seems pretty important. And so why do we study this question as socialists, as revolutionaries? The whole point, of course, is not just to understand the world, but to change it. But without a coherent philosophical framework, our socialism can only be ultimately utopian, not based on an understanding of the material reality of society. In that sense, with Marxism, philosophy becomes a practical subject. Socialists, communists, and radicals, of course, attempted to address these questions arising from the new science in the 19th century onwards. In our tradition, we have Engels, Dialectics of Nature, Anti-Düring, Lenin, hurriedly written, but I think quite brilliant and exhortating materialism and empirio-criticism. Lukács grappled with some of the philosophy of dialectics and I think got it wrong. and Althusser reviewed Lenin and philosophy. Engels' great work, he looked at from the Greek to the Renaissance, didn't really look so much at the Arabs, a little bit at Arab science, but didn't really touch on Chinese and Hindus at all. And of course, the legacy of geneticist and biologist JBS Haldane is also worth considering. Haldane was a member of the CPGB. He railed against enforced Lysenkoism, as been mentioned earlier, the Stalinite dogma that genetics was incompatible with dialectics. Lysenko said that random mutations in genetics were just not possible. Science is the enemy of randomness, Lysenko said. How fundamentally wrong he was. We now know from quantum mechanics that randomness, or as Einstein put it, God playing with dice, is fundamental to matter. In 1927, writing Impossible Worlds, Haldane said, "My own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose." And we've got the work of Stephen Jay Gould also be put into this broad field of understanding philosophy of Marxism and scientific knowledge. So today, while there is a mountain of research into the application of quantum mechanics, work has been to create quantum computing, work is multi-billion-dollar investment and companies now being born, work is being done to push the boundaries of the standard model of particle physics, the search is on for dark matter, neutrinos, the skies are about to open up to petabytes of data in radio astronomy when the Square Kilometre Array telescope opens in just a couple of years in South Africa and Australia. Foundational research, however, on this issue is still seen as a side issue. Some people are doing, but they're still seen as quacks, cranks. People think something you do at the end of your career, you do at the beginning of your career, you won't have a career, is kind of the idea. Most of the modern Marxist currents pay little heed to these questions, and the only ones that have tried that I could find, RCP, Alan Woods, and Ted Grant's Reason and Revolt, the SEP, World Socialist website, a little bit, but it's terrible. If you read it, basically it's to close down any questions and to assert basically, therefore Marxism is correct, next business. So while it may be an influence, Grant actually tries to suggest Heisenberg's position on this, which was probably more Copenhagen than Einstein. He really went with the utilitarian. Heisenberg, who tried to build the bomb for the Nazis, or did he? So it tried to argue that it was Heisenberg's father's background in 1918 suppressing the Bavarian Soviet that led him to having an idealist interpretation of quantum mechanics. Now, that all feels a little bit like blaming World War II on Hitler's potty training to me, but who knows? But Grant basically says scientists can't resolve the quantum quandaries as they don't understand dialectics. Maybe, but I mean, I think that's also pretty spurious. Then they just engage with what I would call hand-wavy sophistry. Listen to this guy called Harry Nielsen writing in Marxism or Marxist.com in 2015. Does the path of an electron exist? Yes, providing that motion is understood dialectically. There you go, solved. That path is the trajectory along which the particle moves. When the particle is in motion, it is not in any one position. It is in the process of moving from position to position. Okay. It moves along a definite trajectory, but to say it is here or there at some point in time means nothing. It is moving from here to there. It is the confusion that comes from an undialectical understanding of motion, the attempt to say that the particle is here at a particular point in time that is exploited by Heisenberg to develop the mysticism that the path does not exist. Okay, there's some truth in there, but it's the whole language and approach is to just say we're right, they're wrong, next business. In Reason and Revolt, Grant and Woods, the laws of quantum mechanics fly in the face of common sense, i.e. formal logic, but are in perfect consonance with dialectical materialism. There you go. Take, for example, the concept of a point. Now, all traditional geometry is derived from a point which subsequently becomes a line, a plane, a cube, etc. Yet close observation reveals that the point does not exist. The point is conceived as the smallest expression of space, something that has no dimension. In reality, such a point consists of atoms, electrons, nuclei, photons, and even smaller particles. Not so sure about that. Ultimately, it disappears in a restless flux of swirling quantum waves. And there is no end to this process, no fixed point at all. This is the final answer to the idealists who seek to find perfect forms which allegedly lie beyond observable material reality. So Einstein, Heisenberg, Bohr, all they had to do was read a bit of Ted Grant and they'd be fine. But the fact is if we interfere in the trajectory, which is indeterminate, our act of intervention produces a concrete but random outcome. This is the great measurement problem that we face. What I think is more exciting about this question, what is matter, how does it work, is we don't really know. As Haldane implies, we can never fully know. There are many prosaic responses to the question, but it's more interesting than that. The central idea that keeps recurring to me as I prepare for this is that motion is intrinsic to matter. Matter does not exist without change. Philosophers, of course, have pondered this question for the entirety of human existence, and it's led to different atomic models. So, atom means indivisible in ancient Greek, I believe. And this was the model developed by Leucippus and Democritus. Matter is comprised of the full and the void. Everything is comprised of atoms which are in constant motion. Atoms were conceived of solid, indivisible, and unchangeable units of matter of the four elements: earth, air, fire, water. So wrong, but maybe not that wrong. Aristotle didn't like this at all. And Aristotle's view won in antiquity until the 19th century, really. Matter's continuous, it's infinite, it's naturally at rest, and the idea of a void is utterly repugnant. For centuries, matter was considered continuous. It wasn't really until Boltzmann, Rutherford, and Einstein that matter was seen as discontinuous, confirming the full and the void. We kind of say that most of matter is now empty space. It's not quite true, but Rutherford showed that by firing into subatomic particles into gold atoms, and in general, they just went straight through. Occasionally, they would go bing off because they hit the nucleus. Most of the time, they just went through. And this upended this model of the atom. J.J. Thomson, who discovered the electron, in 1904, he proposed what's called the plum pudding model. Basically, you have a clump of positively charged matter and potted through are electrons. Rutherford's experiment showed that that wasn't the case. And he developed what we see as the common cartoon picture of an atom that we have now. A nucleus with electrons around it. But the problem was, why didn't the electrons all just collapse into the positive? And this is where Niels Bohr came in, and he said that their orbits are quantized. So the new quantum mechanics came in, and basically electrons can only exist at discrete energy levels around the nucleus. How do they jump from one to the other? Energy comes in, energy comes out, usually in the form of a photon. That's what happens when light beams, so that is kind of where we went, but we kept going. This is actually what hydrogen looks like. If you put different energy levels into a hydrogen atom, creates all these quite weird, these are probability clouds. So the redder it is, the more likely you are to detect an electron in that point. Now there's only one electron around a hydrogen atom. So you put more energy in it, it changes the wave patterns. Now this is just the probability of where you'll find it. You cannot, if you take one measurement, you don't know where the electron will be. But if you take 1,000,000, this is the probability density that you will find. So again, you get this non-determinism. And I don't know if any of you have seen this.
Describe you the effect of cymatic frequencies on matter.
So the universe is made of waves, and at different frequencies, it has different physical impacts. This is a book just come out this year, highly recommend it. Waves in an Impossible Sea. It looks at the field theory of matter and how existence emerges from all these fields. The Higgs, I mean, the number of different fields we have. There's the top quark field, the Higgs field, which you may have heard of, Higgs bosons. The Z field, the W field, the bottom quark field, the tau field, the charm quark field, the muon field, the strange quark field, the down quark field, the up quark field, the electron field, probably heard of electrons, neutrino fields, there are 3 of them, the gluon field, the electromagnetic field, that creates the photon, and the gravitational field. Now, there's an idea that there could be just one field behind all these fields, but we don't know. So what is it we're observing with these clouds of probability? I recently attended a debate at the University of Sydney between philosophers and physicists exploring the question of quantum matter and quantum mechanics and matter. The presentation by one of the physicists struck me. He's a particle physicist who does experimental work at CERN, where the Large Hadron Collider is. He pointed out that using today's experimental machinery and equipment, we can isolate atomic particles to study their properties. We can isolate single ionized atoms and indeed single electrons in magnetic fields. We can prod and poke them, analyzing their physical properties, to the nth degree to find out. But it struck me, that's not what matter is. Matter doesn't comprise of a collection of isolated particles. Matter fundamentally is a relation. It's a relationship, a continual process of motion of relationships. In Carlo Rovelli's great book, Helgoland, which I highly recommend, The Strange and Beautiful Story of Quantum Physics, the Italian theoretical physicist based in Marseille expands on his idea that matter makes no sense unless it is understood as a relation. Specifically for quantum mechanics, he argues the quantum state of a system must always be interpreted relative to another physical system. He calls this the relational quantum mechanics, which, while not a complete answer to many of the questions raised by quantum physics, provides clues to solve the non-locality paradox in particular. I suppose in a category more, a relational category more familiar to this audience, class is not a category, but a relation is a relation. You can't understand social class. I mean, if boring debates of, oh, what's your class background? Oh, but doesn't your grandfather a landlord? Or, you can't, if you try and narrow it down to an individual, you can have, miners who are earning 200,000 a year, who own investment properties. Are they working class? Are they? So it makes no sense almost at that individual level. So back to our knowledge of matter and some questions. And I won't go into these, but if the dominant cosmological theory of the Big Bang is correct, and that's only 100 years old, that idea, how did the universe arise from nothing? It's worth reading this book, Lawrence Krauss, Universe from Nothing. Apparently got cancelled for being a sex pest. I heard. But still a good book. If the entirety of the cosmos emerged from a singularity, a point of zero volume, of infinite density, why is it that matter is conserved in the universe? Why is our universe made up mainly of matter and not antimatter? It should have been equal amounts of both, but there was some weird asymmetry. Why is baryonic matter, that's atoms, the matter that we know of, seemingly only 5% of the universe? That's sun, stars, butterflies, chairs. The rest of it seems to be dark energy, dark matter. Why are we not happy with the standard model of physics, which works so well but has limits? Does the Higgs boson provide neutrinos with mass? We don't know. Can the supersymmetry implicit in string theory unite these theories? We don't know. String theory is a great idea, but has no testable qualities at the moment that we know of. So what is all the other stuff referred to as dark matter and dark energy? We don't know. Feels a bit like the ether. We know something's going on, but we haven't found it. Why does entangled matter seemingly communicate with itself instantaneously across distances? Why are physical laws seemingly consistent? We don't know. That's the really exciting answer. We don't know. So the materialist concept of matter and knowledge. As materialists, we accept the independent existence of matter. Epistemologically, we accept that an objective reality exists independent of our existence, independent of human or any other form of consciousness. And we accept, I think, that this objective reality is knowable, as limited as our senses are, but it's never final or complete and never can be, thinking of what Haldane said. Look, I'm a complete amateur at this, philosophically and scientifically, but I've been a science journalist for a number of years and a science communicator. Look, this talk's bound to have many mistakes in it, so feel free to come back at me. Back to ancient Greece. Two philosophers of the ancient world before the rise and dominance of Socrates, as he was called in Bill and Ted's Excellent Adventure, were Parmenides of Elea and Heraclitus of Ephesus, both who lived around 500 BC. Very little remains of their work. The cynic, what's his name, Diogenes, wrote about them, so they were known about. Parmenides held that the universe and matter are immutable. Well, let's go. There we go. Parmenides held that the universe and matter are immutable. His was the philosophy of stasis. Whatever is, and what is not, cannot be. Everything is continuous. By stark contrast, Heraclitus, who likely wrote before Parmenides and may not have been aware of this guy, he argued the philosophy of flux, and his words are, well, we better know, everything flows, nothing abides, everything gives way and nothing stays fixed, everything flows, nothing remains, all is flux, nothing is stationary. He reportedly, apparently came up with the idea that man never steps in the same river twice because of its constant change. So central to this idea of flux was the notion that the world was always becoming, never being. I find this idea quite attractive. Panta rei is the ancient Greek phrase, everything flows. Later, Greek philosophy inspired by Plato concluded that, well, both were right. But Plato said that the immutable essence of all things is change itself. Okay, good. But rather than see the universe as a whole, Plato and much of Greek philosophy separated the world into the realm of forms, which is perfect, going back to Ted Grant, cubes, perfect shapes, and from which we get the idea of the Platonic solids, who associated them with the classical elements. So the world, they split the world into the perfect world and the not perfect world, which I think does Heraclitus and no favours. Engels said of the ancient Greeks, thus we have once again returned to the point of view, the great founders of Greek philosophy, the view that the whole of nature, from the smallest element to the greatest, from grains of sand to suns, from protista to men, has its existence in eternal coming into being and passing away, ceaseless flux, in unresting motion and change, only with the essential difference that what for the Greeks was a brilliant intuition is in our case the result of scientific research in accordance with experience, and hence also it emerges in a much more definite and clear form. And Engels also in the Dialectics of Nature looks at how the Renaissance led to the dictatorship of the church in Europe over men's mind being shattered, directly cast off by the majority of the Germanic peoples who adopted Protestantism, while among the Latins, a cheerful spirit of free thought taken over from the Arabs and nourished by the newly rediscovered Greek philosophy took root more and more and prepared the way for materialism of the 18th century. So he traces this relative golden age as rising with Copernicus, who overturned the Earth-centered view of the universe. He did it on his deathbed, so he didn't get hung, drawn, and quartered, but who can blame him? And he actually argues it died with Newton. You can tell Engels did not like Newton. I mean, people say Newton was the first great modern scientist, but in many ways he was the last of the alchemists, last of the obscurantins, as brilliant as he was. And this led to an ossification of knowledge through the 17th and 18th century, overturned really not by scientists who were just stuck in their mind. If you look at, God was everywhere in the science of this period. Copernicus at the beginning of the period, says Engels, writes a letter renouncing theology, and Newton closes the period with the postulate of a divine first impulse. So people like Newton and others knew that things were constantly moving, the planets and everything moves. Where does the first motion come from? Well, that's easy. God just started it. God gave the first push. Oh, well, that's that solved. And that was kind of the dominant idea in the 17th and 18th century. So although he developed a revolutionary theory of motion and gravity, it obscured its origins in theology. We then see a systematic ossification of knowledge, which was not shattered by the scientists, but again by philosophy. Immanuel Kant developing the idea that the solar system emerged from a glowing nebular mass. I actually didn't know this when I was doing research for this, but Kant developed the idea of the origin of the solar system. And Engels says the question of the first impulse was abolished. The Earth and the whole solar system appeared as something that had come into being in the course of time, a revolutionary idea. So the constant motion of matter has returned to the central question of science. The 19th century saw tremendous strides in scientific knowledge alongside the development of industry, evolution, and the work of Max Planck, which opened the revolutions of relativity and quantum mechanics in the 20th century. But before we get to those, a quick aside on knowledge. Firstly, how do we know matter is there? We do this through our consciousness and our sensual interaction with the universe. In his screed against the Marxists, Bogdanov and the like, in Materialism and Imperial Criticism, Lenin took many to task who argued that all we know is the sensual world, not the objective world. He rejected this agnosticism that said we can only know our sensual interaction with the world. We'll see this again. Many of the quantum physicists of the 20th century basically argued that. Lenin argued that this sensual interaction produces images of the soul and ultimate objective reality, not ultimate in the sense that it has already been explored to the end, but in the sense that there is not and cannot be any other. In short, matter exists independently of us. And further, we can know this, but to borrow from Heraclitus again, knowledge is in a constant state of becoming. So if we add to this our understanding that matter is not merely a collection of isolated objects, but intrinsic to matter is relations between objects, we start to get a very dynamic understanding of matter. I think it is this that is missing from some of Lenin's cruder categorizations. For instance, when he defines matter as a philosophical category denoting the objective reality which is given to man by his sensations and which is copied, photographed, and reflected by our sensations while existing independently of them. I mean, it's not wrong, but it lacks some of the dynamism of that matter energy display in experiment. And Lenin couldn't have known that as it was happening at the time he wrote. And also lacking really in that is the idea of humanity as part of the scientific process. It still sees humans as the observers of science. Quantum mechanics has completely upended that once and for all, which I think is a tremendous step forward. So back to the debates on matter. Within 2 years of our old friend de Broglie, Erwin Schrödinger had published his famous equation that described the wave mechanics of quantized matter. Heisenberg had developed his uncertainty principle. And in 1935, quantum entanglement was developed as an idea, actually in a negative sense, by Einstein, Podolsky, and Rosen. So Einstein kept trying to come up with ideas to ridicule and find the limits of quantum mechanics and say, well, the logical outcome of your theory is if you have particles that become two particles that are described by the same wave function, you could theoretically separate them and they would still be part of the same wave function over infinite space. And they tried to ridicule this. But of course, that's true. It's been proven in experiment by a guy called John Bell from Ireland in the 60s, came up with the idea of a Bell test. And this is shown. So the most counterintuitive, this is the most counterintuitive ideas of quantum mechanics, I think, is entanglement. That by inducing a physical relationship between two objects, photons, or whatever, splitting a photon while they retain entanglement I described by the same equation, we can separate these objects, and so long as they are not decohered, i.e. interfere with other parts of matter, they remain entangled. They remain in some sense the same system. And a physical operation on one of these objects will instantaneously cause an outcome on the other, even if they're theoretically on the opposite sides of the universe. It's quite challenging. But in one sense, why not? This evokes, I think, Newton's first law of inertia. Every object perseveres in a state of rest, this is Newton, or of uniform motion in a right line, except insofar as it is compelled to change that state by forces impressed thereon. This is about gravity and force at the macro scale. Now, special relativity is not broken here is because the only way you can exchange information about this instantaneous change is at light speed. So you can't cheat the cosmic constant, which is light speed. The three sort of big foundation, I'll try and finish in the next 10 minutes. Heisenberg's uncertainty principle came out of this, and that was 1927 as well. Basically, this is where something is moving. There's a limit to how much we can know about that. Schrodinger's cat, again, something that emerges negatively. Schrodinger was a realist, a materialist. He was on Einstein's side in the arguments in the 1920s. And he basically said, well, if something exists in a superposition, like if an electron is up or down, and it actually is both until you measure it. And it's only the act of measurement that you get an outcome, is the sort of Copenhagen understanding. He said, well, this is ridiculous because if at the macro scale, if you had in a box a quantum object decaying radiation and you didn't know when, it was completely randomized, quantumized, and it would trigger the release of poisonous gas in a box with a cat in it, and you don't know until you measure the cat, the state, the quantum state of the cat. It exists in a superposition of alive and dead. And this was to ridicule the idea, but of course, superposition has been shown to exist as well. And this is entanglement, the idea that two objects are effectively described by the same wave function.
You know, many of us who came from this generation, many of us who came.
I just thought, this is Leo Susskind. He's one of the great sort of proponents of quantum mechanics. He's a great teacher. His lectures from Stanford are some of the most watched lectures on quantum mechanics. He's written books on it. Anyway, this is what he says.
From this generation as users of quantum mechanics began to question, but we never really did have a good idea of, in my view. I think it was maybe Feynman said it very well. He said, I'm so confused about the question that I can't even tell if it really is a question. I feel that way. The whole thing is so confusing that I can't tell whether it's a real question or it's just something in the human brain that just doesn't want to accept how quantum mechanics works. Maybe the brain is the way it is because of evolution. Can you imagine a brain having been involved, which was very, very good at quantum mechanics and saw uncertainty all over the place and knew about tunneling and knew that if he went through a wall, there was a finite probability. I think that creature would be dead in no time at all. So maybe, so maybe it was important for the evolution of the species that it rejected quantum mechanical thinking. I happen to think maybe that's right. But for one reason or another, most of my friends and my colleagues who have thought hard about this just come away puzzled. Each one comes away with his own interpretation of quantum mechanics. None of them to me are very compelling. What is compelling is there's something puzzling that we, I can't even say we don't understand it because as Feynman said, it's not even clear to me that there is something to understand.
So if you're feeling confused, you're not alone. But I think what for me, he's one of the better guys, and I think he's showing that there's something more to know. Unlike many of the thinkers of the 20th century, like Werner Heisenberg, this is important. Science has ceased to be a way of peaking unnoticed in the world, and instead humanity's become an actor in the interplay between man and nature. Okay, that's good. That we assert that. But it led to this complete idealistic backlash. Stephen Hawking saying mental concepts are the only reality we can know. There is no model independent test of reality. That's Hawking, who's apparently a very rude man. Apparently used to deliberately drive over people's toes in his wheelchair at Cambridge if he didn't like them. Someone I know I work with me. Niels Bohr, the world is revealed by experience, by measurement, okay? And this is the only reality worthy of the name, right? Okay, I'm not happy with that. John Wheeler, who's one of the crazy ones, no phenomena is a phenomenon until it is an observed phenomenon. It doesn't exist. It's a super idealistic. Now, this is Bohr and Heisenberg in 1934, actually. But in 1927, at that big conference, they presented a paper that said, while we consider a quantum mechanical treatment of the electromagnetic field as not yet finished, we consider quantum mechanics to be a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. Now, this reminds me of what Lord Kelvin was accused of saying. Oh, it's all finished. We don't need any more. Which I think is clearly not the case. Now, where does this idea come from? In Einstein's Unfinished Revolution, a book by realist physicist Lee Smolin from the Perimeter Institute in Canada, he cites science historian Paul Foreman, who argued after World War I, the ideas of chaos and irrationality argued by Spengler were very dominant amongst this milieu. We heard about Spengler earlier in the week with Ben. And a study of Foreman's work by Berkeley historian Catherine Carson and others states, fashionable philosophical and ideological treatises, including Oswald Spengler's Decline of the West, mobilized the educated public against ideas of rationality, progress, modernity, materialism, popular prior to the war. In this new romantic intellectual atmosphere that elevated intuition and celebrated irrationalism, many academics wavered in their attachment to the rationalist values heretofore central to the practice of the exact sciences. His study found that some leading proponents of the quantum revolution entering a pact with anti-rationalist conservative ideological currents, whereas those physicists who upheld the values of causality and reason, often rhetorically dismissed at the time as scientifically conservative, were frequently aligned with progressive forces supporting the Weimar Republic. So this posits it in, Lysenko, we've already done that. So is it a coincidence that the emergence of Copernicus and his proclamation of a heliocentric universe coincides with the Reformation and religious revolts against papism? Is it a coincidence the ossification of modern science in the 17th and 18th centuries, the conflation with mysticism, were at the time of emergent autocratic monarchisms throughout Europe? How much of a parallel is there that the revolutionary ideas of Darwin, Marx, Einstein and the birth of quantum science was in an 80-year period from 1848 to 1928 that witnessed revolutions, industrial, political, counter-revolutions and wars across Europe? It's a good question, I think. For me, one of the great contributions of quantum mechanics is in the context of this talk, is that humans are no longer merely objective observers of matter and nature. We're not independent of nature. This should be seen as a step forward, despite the idealistic counter-revolution this has triggered. Many in the last century have tried to fight against it. One was a guy called David Bohm, a student of Oppenheimer. He was briefly a member of the CPUSA, but he was poo-pooed by Heisenberg and Oppenheimer later. Irish physicist John Bell was a realist, even though he developed the test that proved non-locality. I've mentioned Lee Smolin. There's other people like Robert Speckens at the Perimeter Institute in Canada. So quantum mechanics is brimming with the potential for a deeper understanding. And I won't go into the gravity as well, theories of gravity. I'm coming towards an end. All the interpretations, some of the most bizarre ones, which people like Brian Greene are sympathetic to, is this idea of the many worlds interpretation. When you do make a quantum measurement, what happens to the other potentiality? Well, they argue it happens, but in a different universe. So a quantum measurement creates another universe. There are people who seriously believe this. Very smart. Sean Carroll is another one. They seriously believe this. And it's easily countered by the quantum roulette thought experiment. I don't know if you know this. Basically, if you were to put a gun with one bullet in it, and basically someone said, you can fire that at your head, and if you don't die, I'm going to give you, or there's only one empty chamber. I will give you $1 billion, and you line the money up. Well, if you believe in the many worlds, you're just going to blow your brains out. It doesn't matter, because there's going to be one universe where you end up with the house and the $1 billion. So it doesn't matter, does it? There's the wave function collapse idea, that they see the wave function as a physical thing. Roger Penrose, who some of you may have heard of, he argues that as this is a doorway to uniting gravity and quantum, as quantum objects increase in scale, gravity starts to impact them, and that's why the collapse happens. There's lots and lots and lots of ideas. Einstein said quantum mechanics is very worthy of respect, but an inner voice tells me this is not the genuine article after all. The theory delivers much, but it hardly brings us closer to the old one's secret. In any event, I'm not convinced that he plays with dice. Niels Bohr told Einstein to stop telling God what to do. So we've seen, and this is what they came up with. This is close to the grandiose statements of Michelson in 1887. Most of the realists hold out that there are more revolutions to come, and how could that not be the case? And conclusions. So for the left, for Marxism, I want you to consider this talk as underlining that our materialism is open-ended. It is scientific. It is evidence-based. It is not dogmatic. It takes theory seriously. It takes philosophy seriously, not merely as some sort of moral compass or framework to comprehend the world, but as an iterative and collective system to develop theory as a constantly developing guide to our activity in the world. Most of the left operates as if the theory's done, we might need some tweaks. Like the activist left, we don't need to think about theory. We just open Chris Harman and he tells us what to do. Others, perhaps like Platypus and others, they regard theory as their only praxis. We just sit around in comfortable rooms and talk about angels on a pinhead. Oddly, current quantum physics seems stuck in a similar malaise. There is a rapidly growing body of published scientific literature on quantum computing, quantum engineering. I'll touch on this in my AUKUS talk tomorrow. Quantum information theory, but quantum foundations still regarded as quaint or for cranks. But we cannot develop good and relevant praxis without constant reiteration with theory. Some of you may know, and I'll end on this, Paul Maddock was a council communist and anti-Bolshevik. In 1960, he wrote on